Hey everyone, welcome back. So today we're going to do node voltage and mesh current review. But before we start that, I just want to talk a little bit about general circuit analysis. So all these circuits that we've been looking at are linear circuits, meaning that their IV characteristics are lines, vertical lines for voltage sources, horizontal lines for current sources, and any other sort of resistor is a sloped line. And so here is kind of a general box format. We don't know if these are sources or if these are receivers, loads, resistors, whatever they might be, but each of them is a linear element. And so if we have any connection of these linear elements, we can solve the circuit completely given the element equations that we have and the circuit equations that we have. And essentially the element equations boil down to either Ohm's law or the vertical or horizontal characteristic lines of the sources. So these are all our IV curves right here. And then the circuit equations that we have, they're based on Kirchhoff's laws. So how does current behave at a node, and how does the voltage behave around a loop? And so that's what we're trying to do. So here's an example circuit. And so if I want to find everything out about the circuit, everything I need to know about this circuit, I would need to know the voltage and the current for each of our elements. And so we have 1, 2, 3, 4, 5 elements. So I need to have 10 things to find. So there's 10 unknowns. And I've listed them over here on the side here. Since we have 5 elements, we need 5 voltage drops or rises. We need to know the differences across those elements, and 5 currents through those elements. And if I know all of that, then I know everything I need to know about the circuit. So you know from your math, linear algebra, that since we have 10 unknowns, we need 10 independent equations to relate these unknowns. And if we have those 10 independent equations, then we can solve them simultaneously, and we'll know all the values. And so we get 1 or 5 of these equations here, in this case, from the 5 element equations. So if I have a source, I know V equals V naught. If I have a resistor, I can write in Ohm's law, I is V over R. And so we write these for our 5 elements, or every element that's in our network. And so that gives us 5 of the 10 that we need. We still need 5 more, and we get those from the circuit equations. So if I look at KCL for this example, we have 1, 2, 3, 4 nodes in our network. And so we'd be able to write 4 KCL expressions, 1 for each of the nodes. And that would give us 4 equations here. It turns out, though, that one of these is not usable since it's just the combination of the other 3. And so we have one redundant one that's not independent. So we only get 3 from these equations. So we have 5 plus 3, we have 8 of our 10. And then we can look at the KVL. We have 3 loops, 2 meshes, and then a loop that goes around the outside. And so we get 3 more equations from those, but it also turns out that one of those is going to be redundant. And so we get 2 more equations from that. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all circuits, linear circuits, can be solved in this fashion, where we can get the element equations, the KCL equations, and the KVL equations, and they give us enough independent equations to solve our circuit. So node voltage and mesh current are different ways to characterize the circuit. Instead of looking, and for node voltage, instead of looking for the currents through each of the independent elements here, we're going to look through the currents for each of those, but instead of looking at the voltage drops, we're actually going to look at the node voltages. So that reduces the number of unknowns that we have from 5 to 4 in terms of our voltages, and we have 9 unknowns if we were going to solve this by the node voltage method. Now, that might seem like we've reduced the number of unknowns that we need to know everything about the circuit, but ultimately we're going to want to look at these voltage drops, so we do have to go back to those 10 unknowns eventually. And so here's another look at the same circuit, but from a mesh current standpoint. In a mesh current, we look at the loops and find there's 3 loops here, but we're only going to look at these 2 currents in the meshes inside these open windows, as we described before. And so we take all of the currents, those 5 currents, and actually reduce them to just 2 mesh currents. We have our 5 voltage drops and our 2 mesh currents. So this turns into 7 unknowns. And so it's still, again, an illusion because we have to expand these mesh currents into our element, our branch currents eventually. but it is a way for us to kind of systematically do this with a reduced number of unknowns. And then when we look for particular branch currents, we can use our mesh currents to find those. So that's just a basic overview of our general circuit analysis and using our independent equations from element equations and circuit equations to figure out what we need in terms of finding V and I for every element. Now, so you guys are kind of familiar with node voltage analysis and mesh current analysis, at least in an overview sense. And there's a question of which one is better to use in each situation. I would say the short answer to that is to just use the one you're most comfortable with. So I generally like to just go with node voltage analysis. But if you wanted to do something such as looking for the one that reduces the number of unknowns, you can see in this example for this circuit, we actually have 9 unknowns if we do node voltage, and only 7 unknowns if we do mesh current. So some would argue that that would be the way to go. The other thing you have to consider is what are you actually looking for? If you're looking for a voltage, then it's easier to find the node voltages and then just do a difference of node voltages, and you get a voltage drop across one of the elements. And if you're looking for a current through one of the elements, then it's actually easier to do a mesh current. So then you would have the mesh currents, and then it's a simple relationship to find the current through any one element. So it's really kind of dependent upon what you're actually looking to analyze. So here's another circuit construction that I wanted to show you. In this case, we have 4 meshes, but only 3 nodes. And so in this would be, you would have actually less nodes than you would mesh currents. And so that would be, maybe selecting a node voltage because you'd have less unknowns. So that's a basic overview. Just wanted to kind of share that with you. So these 2 techniques, node voltage and mesh current, are ways that we can simplify and proceduralize solving these independent equations and do that in a fashion that's easy to do. So we're going to do node voltage first, and I want to remind you of the rules. So for the node voltage method, the process here is first we identify and label all of our nodes. We choose one node to have 0 volts, which we call the reference node or ground. And then we solve for any easy node. So if anything is tied to that 0 volts, that we can find a node that has a voltage because of a voltage source, then we want to do that first. Then for any unknown node, we write a KCL equation. We substitute in for the currents in the KCL equation for Ohm's law. Then we're going to solve simultaneously for the node voltages. And then from there, we can use Ohm's law to find the branch currents, or we can use a difference in node voltages to find the branch voltages. So I want to do an example here. Again, I'm just going to talk you through the example, and you can always pause it and take a look back at it later. Since we are pretty familiar with node voltage, I chose one that was a little more complicated. This one has a supernode and a current source, and so we can look at what's happening and if we have that kind of situation where that's a supernode right there. We have a 4.8 volt current source right here. We have resistor 1 is 5 ohms, resistor 2 is 2.5 ohms, resistor 3 is 10 ohms. We have a 5 volt voltage source with its polarity marked. We have a resistor 4 is 2.5 ohms, resistor 5 is 1 ohm, and then we have a 12 volt voltage source with its polarity marked. And so let's go through our steps. So first thing is we're going to identify our nodes. So all the nodes have been boxed, and we have 1, 2, 3, 4, 5 nodes. And we're going to label them. So I've labeled them A, B, C, D, and E. And then I'm going to choose a reference node. So the reference node here is 0 volts at the bottom. So I chose that because it was at the bottom of my circuit and bottom of 2 sources, the current source and this 12 volt voltage source. So I'm hoping that this is the lowest voltage in the circuit. It doesn't really matter if it is or not, but it makes your numbers a little bit nicer if you do. So the next step would be to solve any easy ones. So any voltage source that's connected to this 0 volt node, I would be able to use to get the voltage of the node that's connected to. So if this is 0, that's 12 volts, and we go from minus to plus, so this is a gain. So node E must have a value of 12 volts. So I've marked these circles in my table. I made a little table here. Node voltages, A is 0, and then E is 12 volts. And so what's the next step? Well, the next step is that I want to identify if I need to use a supernode anywhere. So if I'm going to write KCLs out of C, I can relate the current out of C in this direction to the voltage across this resistor. I can relate the current out of this direction to the voltage across this resistor as well. But since the I of V characteristic of a voltage source is just a vertical line, I don't have any way to relate the current that I'm going to get. This can provide any current that is necessary, so there's no relationship there. So I can't actually write a KCL out of here in terms of voltages, and so that makes a problem. So to overcome this, we actually include that voltage source and the next node in what's called a supernode. And so KCL still applies because I know that any current that is leaving out of C if I add in the currents that are leaving out of D, they're all leaving out of this supernode, and so the rules still apply that you can't generate charge or current inside the supernode, so all of those currents leaving must be equal to 0. The only little caveat is that any currents that are leaving out of D must be referenced back to C. So we're going to kind of use C as our reference node, and then D, since we have this 5-volt source in between, is just going to have the value of C plus 5 volts. And so whenever we write a voltage or a current expression in terms of voltage out of D, we have to use VC plus 5 volts. And so that's shown right there. Okay, so the next step is to write KCLs for our unknowns. We have our unknown B, and you could say we have an unknown C and D, but since we incorporated that all into a supernode, that becomes one unknown, and that is our supernode. And so I'll show you what I mean when we write this. So at B, all of the currents leaving that node must sum to 0. So that's what we're doing here. So the currents leaving the node must sum to 0. So let's look at the paths out of B. So we have a path this way through our current source that's out of B, but the current source says the current's coming in. So we want the current leaving, so we have to take the negative of that. So it's negative 4.8 amps leaving in that direction. What is the current leaving down resistor 1? Well, the current is the voltage over the resistance. So we take the node voltages, VB minus VA over 5 volts. So VB minus VA over, 5 ohms. VA we know already is 0 volts though, so we substitute that in for 0. And then we do the same thing from B to C. So VB minus VC over 2.5 ohms, and we set that equal to 0. So since we always started at B over these resistors, we're assuming that the direction of the current is out, so we assume the polarity is higher voltage at B and lower voltage at the other nodes. So we go VB minus in both of those. So what about the supernode? So I have 4 exits here from C to B, from C to A, from D to A, and from D to E. So I have to write 4 terms in my Kirchhoff's current law expression. So VC minus VB over 2.5 ohms, and then VC minus VA, which is 0, so this is just VC over 10 ohms. And then I have VD minus 0 over 2.5, but VD is VC plus 5. So I have VC plus 5 minus 0, so VC plus 5 over 2.5. That's where we get that. Then I have VC plus 5 minus VE over 1. And VE we know already is 12, so VC plus 5 minus 12 over 1 equals 0. Once I have those, I plug them into my calculator or an online systems solution webpage, and then I get my answers here for my node voltages. So VB and VC are the only terms that are left in these 2 equations, 2 equations, 2 unknowns. VB is 11.35, VC is 5.02. So you should try that on your own to make sure you get those answers. So VB here now is 11.35 volts, VC is 5.02, and I have the relationship of that supernode that VD is 5 volts more than VC, so I can add 5 volts to that, and I get VD is 10.02 volts. So I have all my voltages, so pretty much we're done. The only thing is now if I want to solve for something in particular, a branch voltage or a branch current, then I could do that. So I chose to look at the branch voltage V2. So what is the voltage across R2? Well, the first thing I have to check is what is the actual polarity across this resistor. So I look at VB and I look at VC. VB is 11.35 and VC is 5.01. So the higher voltage is at B. And so the polarity across this resistor is positive at B and minus at C. And so that means the current is also flowing in the direction from B to C. And so I'll do that in my calculation, VB minus VC, so I get a positive answer. 11.35 minus 5.02 gives me a voltage drop across R2 of 6.33 volts. So I can use that to calculate the current through, the branch current through R2. using Ohm's law, I2 is V2 over R2. I already found V2. R2 is 2.5. We get 2.53 ohms going from B to C. I'm also going to look at the branch current I3. So I have 2.53 entering here. What's going on between C and A? So C is higher than A. And so if I want to draw a polarity for R3, it's like that, plus and minus, and we have the direction of the current directed downward. And so VC minus 0 over 10 gives me 5.02 over 10, or about 0.5 amps. And so one thing we're sometimes asked to do is find the current through one of the voltage sources. And since that doesn't have an IV relationship that includes an R, we have to use a KCL to do that. So I've kind of redrawn node C here. I have I2 entering node C, I have I3 leaving node C, and then we have the current that goes through the 5-volt source. So these are the three currents that are operating at node C. So if I want to write a KCL here, I know that the current through the 5-volt source that's exiting here would just be the I2 that's entering minus the I3 that's also exiting. And so 2.53 amps minus 0.5 gives me 2.03 amps that are going through the 5-volt source from C to D. Mesh current method. So in the mesh current method, first thing you do is draw the mesh currents. Then we inspect for current sources that include only one mesh current. And so this is the easy one, just like the nodes that were next to a voltage source. This time we use KVL, so we write a KVL for the remaining nodes, and we want to write it in a way that the sum of the voltage drops is equal to 0. We'll get expressions then where we can solve simultaneously for all our unknown mesh currents. And then from there we can solve for our branch currents as defined by the mesh currents. And then finally we can solve for any branch voltages using Ohm's law. So let's take a look at an example for mesh current. Great. So I have here a 120 volt source with that marked polarity here. We have this complex construct of 2 ohms resistor connected to a node. We have 10 ohms here, 6 ohms here, 3 ohms there, 4 ohms there, and then kind of in parallel to that whole section, we have a 3 amp current source. So let's start with our method. Identify our meshes. So we have 3 windows here, so I'm going to draw my 3 mesh currents, and I'm going to take them in a clockwise fashion, so I1, I2, and I3. And ultimately, I want to get those 3 mesh currents, and then I can find everything else from those. This is a little bit different than the method I've taught you guys last time. This is kind of a simplification. It's a little bit more of a shortcut, but I think it's a little bit less understandable. But since you guys have already seen the other version, I'm going to show you this one. Procedurally, it's easier. And so let's show you how this goes. So identify any easy ones. So do any of these mesh currents go through a current source, and they're the only one that goes through it? And yes, I1 goes through this 3 amp current source. So I can right away write this easy answer that I1 is 3 amps. So that leaves us with 2 unknowns. So we're going to need to write 2 KVL loops. So I'll write the first KVL loop around mesh 2. And so this is the idea of the sum of the voltage drops are equal to 0. So sum of voltage drops are equal to 0. So that's important, because if we have a voltage rise or voltage gain, that should be a negative number. And so I'm going to start here at this node, and I'm just going to go around this loop. So as I go through this source, this is a voltage gain or voltage rise of 120 volts. So when I write that as a drop, it's minus 120. And so now we're going to assume that through any resistor that the direction of the current is in the correct polarity for a voltage drop. And so generally the current will flow in the direction such that it drops through resistors. So let's ignore the other currents here and just look at I2. So I2 will drop through the 4 ohms, it'll drop through the 10 ohms, and it'll drop through the 2 ohms here. So I'm just going to write it in that fashion. Okay, so I2 is going through resistor 4, but on the other side here we have I1 that's also part of this loop that passes through the 4 ohms. It goes in the other direction, so that would be a voltage rise. And so we're going to take I2 minus I1, that'll be the effective current going through the 4 ohm resistor, multiply that by the resistance, and we get the voltage drop. So I got 4 ohms I2 minus I1. So a shortcut for this and understanding like the procedure is just that you take the mesh that you're looking at, and if a current is going in the same direction as the mesh, you add that current to it, and if the current of another mesh is going in the opposite direction, you subtract it. So I got I2 minus I1 times that 4 ohms. Now at the 10 ohm resistor, I got I2, I3 goes the opposite direction, so I minus I3 multiplied by that 10 ohms. And then in this last one, I only have I2, so it's plus 2 ohms times I2 equal to 0. And so we're adding up the voltage drops around that loop and setting them equal to 0. For the third mesh, same sort of thing. It doesn't matter where you start. I started here at this node. And so I have I3 going this way minus I2 going this way through that 10 ohms. So it's 10 times I3 minus I2. And then I have I3 going to the right across the 3 ohms, I1 going to the left. So 3 times I3 minus I1. And then lastly, I3 only goes through the 6 ohm resistor, so I add that drop. 6 times I3 is equal to 0. These are voltage drops because they're IR, so by Ohm's law, V equals IR, and so we're doing the IR products here. So when I get these two equations, I just plug it into my simultaneous equation solver, and I get that the mesh current I2 is 12.74 amps, and the mesh current I3 is 7.18 amps. So I know this mesh current, and that mesh current. I don't know any of the branch currents at this point because I have to find them by calculating the mesh currents that pass through them. So let's solve for some branch currents. So I can see that I2 going from left to right across the 4 ohm resistor is greater than I1 going from right to left. And so if I want to find the actual current going through resistor, it's going to be I2 minus I1, and the polarity of that, or the direction of that current, is going to be from left to right because I2 is greater than I1. And so I go ahead and solve that. So I4 ohms is I2 minus I1. 12.74 minus 3 gives me 9.74. So 9.74 amps going from left to right. I want to also find the one through the 3 ohm resistor. Again, 3 ohm resistor has I1 flowing to the left and I3 flowing to the right through it. And I3 is greater than I1, so the actual direction of the current is going to be from left to right. And then I can find this as the difference between those two, I3 minus I1. And I do that right here. 7.18 minus 3 gives me 4.18 amps. So I know I have 9.74 amps flowing to the right across 4 ohm resistor. I have 4.18 amps flowing to the right across the 3 ohm resistor in this circuit. What about the voltage drops across our, so this 4 ohm and the 3 ohm resistors? Now I can just use Ohm's law. V4 ohm is I times R. 9.74 times 4 gives me 39 volts. So plus minus, the polarity is correct with the direction of the current arrow, 39 volts. V3 is I3 R3, so 4.18 times 3 gives me 12.54 volts drop across the 3 ohm resistor. Last thing I wanted to take a look at is what if I wanted to find the voltage across the current source right here. So what would that be? Well, we can see that we don't know the relationship between V equals IR because Ohm's law doesn't apply for this one. This is a current source, and so it just has a IV characteristic as a horizontal line, so it can't look for that kind of intersection there. But what I can do is use a KVL here. So I know the voltage across the 3 ohm resistor plus the voltage across the 4 ohm resistor plus the voltage across the source have to be equal to 0. So let's set it up. According to the source convention of labeling our directions, if the current is flowing to the right for a source, then the positive sign is on that side as well. And so this is different than the resistors, assuming that the current was flowing that direction. So when I go around the loop here, I see it's a voltage gain plus a voltage gain, or if I go the other way, it's a voltage drop plus a voltage drop plus a voltage drop. So going around this loop, they're all on the same side with the same sign. So V4 ohms plus V3 ohms plus the V of the 3 amp source, they have to equal to 0. I know the 39 volts is across 4 ohms, 12.54 volts across the 3 ohm resistor, and then I can add that to our variable here. If we solve this, we find that the voltage across the 3 amp resistor is actually negative 51.5 volts. And so although this would be the polarity we expect it to have, it's actually reversed from that. And so there's essentially a voltage drop across the source as the current is flowing through there. So the charges are losing energy as they flow through the source instead of gaining energy as they flow through the source. And so the source is actually not a source at all, it's a receiver. And so you might see that situation where you get something unexpected like that. In this circuit, this source is actually providing energy to this source, and that becomes a receiver. So this might be the case where like you connect something like a rechargeable battery to your circuit, and it's actually taking energy from the circuit instead of giving it to it. All right, that's all I have for today. Thanks for watching. Have fun with homework. Hope you guys are well.